Hello everyone. Welcome again. So today, in continuation with our last lecture, since the beginning of this lecture series, we have been talking about the Drude's model and its relation with the kinetic theory of gases. Now we are going to talk about an immediate application of the Drude's theory, and it's a very celebrated experiment, as you can say, and it has been studied for so long and it's still studied today. So today we are going to learn about the Hall effect. So it's an immediate application of the Drude's theory. So today we're going to learn Hall effect, Hall effect in metals. All right. So it was discovered by Edwin Hall. He was an American physicist. Physicist in the year 1879. So what he was trying to look at, he was trying to understand what happens if you apply an electric field to a current carrying conductor. He was asking the fundamental question that the magnetic field, was it affecting the conductor as a whole, or was it affecting the charge carriers or the electrons? In doing so, he understood that he thought that as because the electrons, it's a current carrying charge carriers, so in presence of an electric field it will feel a force, and does that force act on the whole of the conductor or it's only the electrons? So he thought that the electrons may be drifted to one side of the conductor so that it may affect the resistance. So in case of a transport experiment, what you have is you have a sample. You have a sample. This is the cross-sectional area. So what you try to do is you try to send current in this conductor, and you measure voltage. All right. So try to measure voltage across the sample and you send in current. So you make contacts at the two sides of the conductor. Here you make contacts. On two sides of the conductor, and you try to send in current. So you send in current and you measure the voltage. So what he was trying to basically look at is, does an application of a magnetic field change the path of the charge carriers so that it creates an additional resistance in the resistance what you observe? So he didn't observe the resistance, but it appears as you study in the later part of the course that application of a magnetic field does affect the resistance or the longitudinal resistance. What's the longitudinal resistance? You send in current here and you measure the voltage across the sample in the longitudinal direction along the direction of the applied current. So Hall didn't find it, but it, it's a natural fact that it does depend on the application of a magnetic field. So this Hall effect, it's very important. So the technological application of this phenomena is the Hall sensors, which are used to detect a magnitude of a magnetic field. So it's virtually everywhere. It's in your watch, it's in automobiles to check to check the fuel level of the car. So it's basically everywhere. So the technological advancement, the technological application of this phenomena is widespread, ubiquitous. So we are going to learn today about this very interesting phenomenon. So in Hall effect, all started with the question that what happens to the charge carriers or the current or the resistance when you apply an electric field. Drude expected that, Hall expected that it's going to change the resistance, which he didn't find at that time, but it does happen that the magnetic field affects the the longitudinal resistance. So the experiment is basically done on a thin film of a material, a very thin layer of a material. All right, a very thin layer of a material is taken. Fair enough. All right. So the layer is depicted by this. So this is the thin film of the material, and you send in current across the material. All right. And you also measure the voltage. Measure the voltage across it. All right. So now, in addition to this, you apply a magnetic field. So basically, sending in a current means you apply an electric field across the length of the conductor. So this is your length of the. So you sending current across this direction. All right. And the charges, as you know, conventionally, the charges move along the opposite direction to that of the current. So the electrons, the charge carriers, move along this direction. Now, in addition to this, you now apply a magnetic field which is perpendicular to the plane of the sample. So you apply a magnetic field which is perpendicular to the sample. So now when you apply a magnetic field, it's the applied field. We should denote it by H. But for non-magnetic materials, B and H don't differ by too much. So basically, we will be interchanging between H and B. Everywhere I write B, you have to understand that I am writing about the applied electric field, not the magnetic flux. So this is the magnetic field I am applying. So this is the basic experimental setup for sensing the Hall effect. All right. So what will happen if you apply a magnetic field? In the previous classes, in the last lectures, we have already talked so much about the application of an electric field. We derived the conductivity from Drude's model. Rho is m by n e squared tau. So we derived that. But magnetic field was not there. Now you apply a magnetic field, and what will happen? The, the electrons, the electrons or the charge carriers will experience a Lorentz force. All right. charge carriers experience an Lorentz force. So let me just redraw the setup. So this is your the thin film, the thin layer, and why we are choosing this thin layer means along the z direction it's very thin. So the electrons are bound to move only in one direction, and it's of course in 3D materials, in bulk materials you see Hall effect, but for basic understanding of the phenomena, you know that the electrons are moving only in a plane, so the calculations become easy and it's simplistic. All right, so it's moving in a plane only, in a single plane. So the current is sending current is sent you are sending in this direction. This is where you are making contacts around it, and the electrons are drifting in this direction. Your current is in this direction. So if you draw the coordinate system, our natural choice would be this is your z direction, this is your y, and this is your x. So this is the coordinate system that we are going to work in. So application of the magnetic field, it's in this direction. It's along positive z gap. B vector is B naught z gap. All right. And the velocity of the electrons is along minus y gap. So this is B minus B y gap. Now, what happens? The Lorentz force due to the magnetic field is given by magnetic field is equals Lorentz. The negative charge of the electrons remains outside and V times B. We put in the components is B minus y cap times B naught z cap, which reduces to E V V naught x cap. So what's happening because of this Lorentz force? The charge carriers which was moving with charge carriers which were moving along the minus y direction is feeling a force along the positive x direction. So there's a drift in the positive x direction, so along this direction. So the charge carriers will move in this direction. The electrons, the negative electrons will move in this direction along positive x. So there will be accumulation of electrons. All right. In lieu of that, there will be accumulation of positive charges also. The positive charges are on the other side. Fine. On this side. And there's a drift of electrons from this to this. Drift of electrons from this to this. So what happens if there's a charge separation? There will be automatically an electric field. So you applied an electric field along the longitudinal direction of the sample. In presence of a magnetic field, with the application of magnetic field, you are getting what is a electric field in the transverse direction. All right. So you're getting a, an electric field along the positive x direction. So you send in current along the longitudinal field or the electric field, or you send in electric field along the longitudinal direction. In presence of magnetic field, you get a transverse voltage in the voltage in the transverse direction. So what is this electric field? Our immediate step would be to calculate this electric field. All right. So what we want to take help of is now the Drude's model. You know the equation of motion, Drude's model from Drude's model. All right. Recalling Drude's model, the equation of motion, equation of motion is dp vector dt is equals to minus p over tau plus f of t. So this is the non-spatially varying force. All right. So now this force will be given by the Lorentz force because of the applied electric and magnetic field. So your f of tau t is minus electronic charge into electric field vector minus of electronic charge, velocity of the charge carriers or the electrons times the magnetic field. All right. So now dp dt becomes minus p over tau minus e vector minus e v cross v. All right. So this is fine. Now we want a steady state solution. Steady state solution, which means you are going to look at it in equilibrium scenario. Means you apply an electric or a magnetic field, both are applied at the same time, and you are looking at the sample or the behavior of the sample at a longer time beyond that. All right. So because of that, you are getting a constant current. And let me remind you, if you are getting a constant current, the momentum of the charge carriers should not change. This indicates that dp dt should be 0. So for steady state solution, dp dt is 0. Also, let me remind you, this is the drag term. This is the Lorentz force. Although it's not clear from Drude's theory what exactly is causing the scattering mechanism, but it is scattering, and that gives you the resistivity or the conductivity. Okay. So, for a steady state solution, the force term should be balanced by the drag term. So since dp vector dt is 0, this implies minus p over tau minus e of e vector minus e, this is electron charge, v because B vector is 0. Let me write down the formula of J, which is the current density. Of course, in the previous diagrams, you're talking about I. So this is also I. This is also the current density. So the current density is always in the picture. All right. So if you are sending in a current, you divide it by the area, the cross-sectional area, you get the current density. So now the form of current density, this is your current density is minus NeV. All right. It's also minus NeP vector over N. You can understand what we are going into is we are going to express the V vector and the momentum vector in terms of the current density. All right. So this implies V vector equals minus J vector over NE. On the other hand, P vector implies minus M J vector over NE. All right. So putting it in this equation, so this is our main equation. This equation is our main equation. We get minus the negative sign cancels out for P vector by tau. For the drag term, we get M by NE tau times J vector minus E electronic charge into E vector minus E, which is also, this is also positive. This is J vector by NE times cross product of, and this is 0. Fine. So now you have to put in the direction vectors. So this, let me just simplify, which is M by NE tau J vector minus electronic charge E vector plus this E cancels out, 1 by N times J vector cross B vector is equals 0. So let me put in the directions of this J vectors. So we draw some experimental setup once again. This was your sample. You are sending in current across it. And you measure the voltage in this direction. And this was our coordinate system. This is Z cap, this is Y cap, and this is X cap. Fine. Current is in this direction. Fine. Magnetic field is in this direction. Fine enough. And so J vector is J times Y cap. Fine. My notes ready. And also B vector is V naught Z cap. Fine. So put it in the above equation. We get so M by N E tau times the J vector, which is J Y cap minus E of the electric field vector plus 1 by n j y cap cross b naught z cap, and this is 0. Fine. So now putting electric field on the right side, which is E vector is equals 1 by n. So this is wrong. So this should not be. This should not be. Yeah. This is j b naught x cap plus m by n e tau j y cap. So now you see that the electric field has two components. All right. So you have two components. X component, which is given by Ex x cap, and Y component, which is given by Ey y cap. So E vector is equals 1 by any j b naught x cap plus m by n e squared tau j y cap, and this is your Ex x cap, and this is your Ey y cap. So Ex is given by b naught by ne times j. On the other hand, Ey is given by m over n e squared tau times j. So although you applied an electric field in the x direction, you applied an electric field in the electrons were moving in this direction, electrons were moving in this direction, and your current was in this direction. Now what you get is the electric field was in this direction. Applied electric E applied was in this direction. So now the electric field has two components. One is along the x direction and the other is along the y direction. So the applied electric field was along the y direction. Now, after solving the equation of motion from Drude's theory, you get an electric field that has two components, that is along the x direction and the y direction. So this should ring some bell because this part is very familiar to us, because this is our rho from simple Drude's model. Simple Drude's model. So Ey, along that which direction the electric field was applied, you are getting the resistivity from that in that direction. Alongside it, you are also getting a resistivity or the component in the transverse direction to it. Transverse direction. This is your longitudinal, along the direction in which the electric field was applied. Fine. So Jx, J, so sigma E. So this. So rho longitudinal, rho x direction is your m by n e squared tau. This is longitudinal resistivity, and we got it earlier also. In addition to that, You're also getting a transverse resistivity. This is rho xy is V naught by NE. This is transverse resistivity. This is transverse resistivity. This transverse resistivity is what we call the Hall resistivity, the Hall resistance. This can also be denoted by so the longitudinal resistivity is the resistivity you get along the longitudinal direction, and the Hall resistivity or the transverse resistivity you get along the transverse direction of the applied current or the electric field. Now that earlier we had only electric field along a certain direction, let's say along y cap, and you were getting a voltage along that direction only. Now we have an electric field applied. What you get as an extra term is a transverse resistivity or a transverse voltage along the transverse direction to the applied electric field. So what is happening here? So as I said, so as the electrons drifted from this direction along the positive x direction, there has to be an electric field. There has to be an electric field. All right. So due to this electric field, there will be a voltage developed. Earlier, we were measuring voltage along this direction. Now, along this direction too, also getting a voltage, which is the Hall voltage. And this happens simply because of the Lorentz force. You apply magnetic field and the charge carriers experience a Lorentz force. So in the transverse direction, you're also getting a Hall voltage. So let us see in details what this Hall resistivity is. So Hall resistivity is B naught over NE. This 1 by NE is given a name, which is Hall coefficient. Sorry, this is your Hall coefficient. So the Hall coefficient RH depends on the charge carriers, charge of electrons, and their number density. And their number density. All right. So rho h is RH. So RH times B. So this is one thing. And this RH is 1 by NE. So this is fine. Now, I was talking about the Hall sensors. So if the Hall sensor is an application of this Hall effect. So what it says is that if you have an unknown magnetic field that you want to measure, you measure the Hall voltage, which I'm going to come across. You measure the Hall voltage, and it depends on the magnetic field applied. So indirectly, you have a measure of the magnetic field. This RH is a property. RH is constant for a specific material. RH is constant for a specific material. All right. So if you know RH, you know You measure the Hall voltage as I'm going to derive. You measure the Hall voltage to get an estimate of the magnetic field. You calibrate it. You calibrate it with the Hall voltage. You don't know the magnetic field. No worries. You have the Hall voltage in hand that you can measure with the Hall sensor. So that will give you the calibration curve and you can know the magnetic field. Fine. So from this we can have another parameter. So N will be given by 1 over RH times E. So you can have an estimate of the number density of the charge carriers. From previous lectures, we know that N is given by Avogadro number. So 3 into 10 raised to 23 times the number of electrons, the valence electrons supplied by the metal concerned, times the delta over A. So the A was the atomic mass, so delta was your density. Delta was density of the material. Fine. All right. So this was what we learned in earlier lectures. So you can compare between what was it a real good estimate. Was this formula, was it a real good estimate? Because from experiments you can directly know the number density of the charge carriers in the material concerned. So you can make a comparison between these two. So now you must be thinking about that our RH is 1 over NE. So why not is the negative sign of the electronic charge not, why it's not coming in the formula? So it's just simple. It's just a matter of convention that in our case we took the sample, and this we were sending in current along this direction, and the magnetic field was in this direction, and our coordinate system was like this. This is Z, this is Y, and this is X. So it should have happened that the minus should have come in the Hall coefficient formula, but it's not. Let me tell you, nothing to worry about, because this is just a matter of the convention of the coordinate system. Had I taken this coordinate system, like this is your Z cap. So the current is applied in the X direction. All right. And you measure the Hall voltage along the Y direction. Right? So earlier we were sending in current along the Y direction and measuring the voltage along the X direction. In this case, we'll find that RH comes to be minus 1 over NE. So it's just a matter of convention, and you can understand that the electronic charge which is negative is naturally coming this way. So let me write RH as plus minus 1 over NE as per our convention. So from the Hall coefficient, we can have an estimate of the number density of the charge carriers. Along with it, the sign of the charge carriers is also there. For electrons, as we have talked about electrons only, for just as per the convention, the negative sign appears in the formula for the Hall coefficient. Fine. Now, let me give you some estimate of the Hall coefficient of some materials. All right. So copper, gold, aluminium, and beryllium. So this is minus RH times Ne. So this, let me make it plus, and this is minus 1. This is as per your convention, whatever you can write. So whatever you choose. So for copper, it's minus 1.5. For gold also, it's nearly minus 1.5. Drastically, what you see is that for aluminum, it's much lesser and also positive. And for beryllium also, it is positive. All right. So for the case of aluminum and beryllium, RH is equals to 1 by. So what happens is that for realistic cases, for experimentally measured quantities, this Hall coefficient for aluminum and beryllium and likewise comes out to be positive. So we will go deep as we go deep into this lecture. I'll make this point clear that this was one of the failures of the Drude's theory, that it predicted only that the negatively charged electrons are the charge carriers. So it was a major drawback of the Drude's theory. Before that, let me clear uh, clear it out about the Hall coefficient and the Hall voltage, which is needed when you make a Hall sensor. You measure the Hall voltage only. So in this configuration, let me draw a picture, a schematic. So this is your sample. Fine. Also, this is your sample. Fine. So this is your length of the sample. This is your width of the sample. Fine. And this is your sure. So normal voltage, the longitudinal voltage, V longitudinal, is given by I times R. Longitudinal is equal to V longitudinal by the current you sent. All right. So now rho longitudinal is R times L over A. So the longitudinal current is along this direction. Fine. And the length scale concerned is the longitudinal length scale. Fine. So rho longitudinal is given by V longitudinal by I times L over A. Fine. Which is also M over N E squared tau. Now, for the Hall voltage which you measured, so longitudinal voltage is measured along this direction. Is measured along this direction. But the Hall voltage is measured along the width of the sample. Hall voltage is measured along the width of the sample. Of the fine. Now, VH over I is your RH. We shouldn't write capital RH because it's already defined as the Hall coefficient. So RH is VH times I. So rho H is equals RH times L. Now this length for the transverse voltage or the Hall voltage is your W. Fine. So therefore VH is equals RH is rho H times W, sorry, rho H times A, rho H times A over W into fine. Now rho H is RH times W over A, fine, is equals B naught by NE. Fine. So this is your, so if you know the Hall voltage, then you can derive the magnetic field from it, which is OH is given by this. So if you know RH, so B naught is rho H times NE, which is given by RH times omega by A times NE, is also equals to RH times B naught. So this is RH times omega by capital RH into E. So for Hall sensors, you measure the Hall voltage. If you measure the Hall voltage, you automatically know the Hall resistance. You know the width of the sample. You know the cross-sectional area of the sample along the transverse direction, and you know the Hall coefficient, which is a characteristic property of the material. Alright. So in this way, you can calibrate a Hall sensor. So this is what you get from. So this is fine. This is how measure an unknown field. So to measure the Hall voltage, which is given by VH by R, is resistance for the Hall resistance, and rho H is also RH times W over A. W is the width of the sample. Now you just manipulate these two formulas and you get the magnetic field as a function of the Hall voltage or the Hall resistance. So VH is also given by rho H times A over W into A, right? Now you have the rho H and also you have the B naught. So B naught as a function of the Hall coefficient, the cross-sectional area of the sample, the width of the sample, and the Hall resistance. So you get by that. So you can also automatically write it as VH over I times W by A into 1 by RH. Fine. This all are known to you. Measure some of it, and some of it is known to you. So let me just end this lecture with telling you about the grave limitations or the drawbacks of the Drude's model. So from Drude's model, rho x RH is 1 over NE minus 1 over A. So Drude assumed that the negatively charged negatively charged electrons are only the charge carriers. But this is not the case. Why? Because for aluminum and beryllium, we saw that the product of RH times Ne, it becomes positive. So we have to think about that the electrons are not really the charge carriers there. They're the positive charge carriers, positively charged carriers of charge. All right. In that case, Drude's theory failed in that case in predicting whether positive charge carriers can also carry the current in your sample. So it's a basic failure of the Drude's theory. So the classical model of the Drude's theory was unsuccessful in explaining positive charge. So we need quantum theory in practice, because we would assume that the charge carriers are like hard spheres, classical hard spheres, but it's not. Electrons are quantum particles, they are fermions. So you need quantum theory in practice to explain these drawbacks. And in earlier lectures also, we also talked about this. Another great failure of the Drude theory was to explain the behavior of the insulators. So as you go down with temperature, the resistivity of the insulators diverges, right? So at T tending to 0, rho tending to infinite. That's because rho was m over n e squared tau. Rho tending to infinity means tau tending to 0. So tau was the average time scale between two successive collisions. So this was one electron was undergoing a collision. So this was tau. That's tau tending to 0. The rate of scattering per second will automatically be given by 1 over tau, because the time scale, the thing we were discussing is dt over tau. In time tau dt, what's the number of collisions, or what is the probability that the electron collides. So rate of scattering per second will be given by 1 over tau. So as tau tending to 0, the rate becomes infinity, which is absolutely absurd. This is absolutely absurd. This should not be the case. So the Drude's theory will greatly in explaining the behavior of your insulators. I also said that the positive charge carriers, in that case, the Hall coefficient will be 1 over Ne positive, but for electrons, it's minus 1 over Ne. So for class of materials like the semiconductors, sorry, semiconductors, this is just an info. Depending on the doping, doping concentration, RH can be positive or negative. So we learned today a very interesting phenomenon, which is the Hall effect. It's studied even today, and there are various versions of it, like quantum Hall effect. In addition to the classical Hall effect that we learned today, we will learn in some part of the course. So this was a very great theory, very great phenomena. Experiments are done with see Hall effect in real life experiments. So this was a very interesting phenomena that came directly from the Drude's model. Although the Root model was successful in explaining many things, it was a great theory, but it failed at certain points and it was not able to explain like the behavior of the your insulators at low temperatures will go down with temperatures. It was not able to explain the kind of behavior it shows. Also, the about the presence of positive charge carriers, Root's model was not able to predict that. So with this, I want to end here. So now in coming lectures, we will be learning about the thermal conductivity of a material. So thank you everyone.